All right, so last time we said that you cannot determine delta H for every reaction by calorimetry. Okay, and so what do we do with those reactions that we can't use calorimetry for to determine delta H? Well, what we can do is you can imagine a series of reactions that will eventually convert our reactants to our desired products and simply add the delta H values for each of those steps. So the delta H for the overall reaction will just be the sum of the delta H for all the steps. Okay, so this is known as Hess's Law of heat summation. And if you're going to reverse the reaction, you also need to know that delta H for a reverse reaction will just be equal to delta H for the forward reaction. Okay, and why is that? Um, why is that possible? Because H is a state function. It doesn't matter how you get from your initial state to your final state. Okay, and you also need to know that H is an extensive property, so delta H will be proportional to the coefficients in your thermochemical equation. So if you double your coefficients, then the delta H that you need for that thermochemical equation will just be doubled. Okay, so let's look at this simple examples right here. If you have, I start recording? Yeah, I did. If you have A plus B going to C, the delta H for that reaction is X. What would happen if I were to reverse the reaction? C going to A plus B. It's just going to be negative X. Okay? So, I might be able to carry out a reaction of A and B in a calorimeter, but if I want to know what's the delta H for the reverse process, that's not going to happen. Right? C will not just spontaneously decompose into A plus B if A plus B goes to completion, right? So delta H for the reverse reaction is going to be negative X. What if A plus B gives you C and the delta H for that reaction is X? What if I write my thermochemical equation as 3A plus 3B gives me 3C? What would be my delta H? It's going to be 3X. Now, what if I have this one? A plus B gives me C, delta H equals X. If I were to reverse and multiply all the coefficients by 2, what will be my delta H? Negative 2X. Okay. Here's one. We have A plus B gives me C, and then C becomes D and E. So delta H for the first step is X, delta H for the second step is Y. If I were to combine these two, I have what? A plus B ending up as D plus E. So in fact, I'm adding these two equations. What's my delta H for this one? X plus Y. Right, so it's pretty straightforward. So you can just use those types of manipulations to get the delta H for an unknown reaction. So here's an example, a real example. Graphite plus oxygen gives you CO2. Let's say that's X. Let's say you've figured out that's X. And then carbon monoxide plus oxygen gives you 2 CO2. You determine that to be Y. Right? Now, based on that, can you determine the delta H for the production of carbon monoxide from graphite and oxygen? Now, you might be saying, why do we have to go do these other two reactions? Why not just carry this out in a calorimeter? You can't, because it's not possible to carry this out without any side reactions. If you don't have enough oxygen, you may still get carbon dioxide in addition to carbon monoxide. Okay, so this reaction of graphite with oxygen, combustion of graphite to just form carbon monoxide, that's a very difficult reaction to carry out. It's a very difficult reaction to control. However, if you have graphite and oxygen, you can guarantee that all your product is oxygen. You can carry out this reaction in a bomb calorimeter. You can guarantee that all your product is carbon dioxide by using an excess of your oxygen. Okay? So if you have a large excess of oxygen, you can guarantee that your product is CO2. So this reaction, the first one, can be easily done in a calorimeter, in a bomb calorimeter. The second one, you can put carbon monoxide gas in your bomb. You react with the oxygen, that reaction with lots of oxygen, we can guarantee that all of your carbon monoxide will turn into carbon dioxide as well. Okay, so X and Y here are easy to measure. But the delta H for this third reaction right here, where you have carbon monoxide, graphite plus oxygen just giving you carbon monoxide, that's not easy to determine. So what do? We can use X, based on X and Y, we can calculate delta H for this reaction. What would it be? Note that I've given up writing delta H not sub R here. Okay, if it's kind of obvious that we're referring to the delta H for a thermochemical equation, you can just drop those extra labels. Okay, so what would be the delta H for this one? What would we do? We imagine starting with graphite. Yeah, go ahead.
You still have excess of O2 gas?
Yeah, it doesn't matter. Remember, we're now imagining how we're going to carry this out. So you're going to start off with 2 graphites, right? So you're going to have to multiply this first reaction by 2, right? If you want 2 graphites on your reactant side. And what else do you want? You want carbon monoxide. You don't want to have to deal with O2 because there's 2 reactions that give you O2. Okay, so you don't want to worry about O2 for now. You just want to make sure that you have 2 graphites on the left, and the way to do that is you multiply the first equation by 2. You want 2 carbon monoxides on the product side, so what should you do with the second reaction? Just reverse it. Okay, so what would be the net effect? Well, let's see. If you multiply the first one by 2, you have 2 carbon graphite plus O2 gives you CO2 gas. And so I'm going to multiply my O2 by 2 and multiply graphite and oxygen by 2 and so CO2. So delta H for this is going to be equal to what? 2x. And then I flip the second reaction. I reverse the second reaction. This one right here. So I'm going to put 2 CO2 on the left. Gas gives you back 2 carbon monoxide gas plus O2 gas. And delta H for this is going to be, if I flip reaction 2, what would be the delta H for the reverse of reaction 2? Negative Y. So what happens if I add these 2 reactions? CO2 cancels out, right? And I have 2 carbons, graphite, plus 2O2 gas yields 2CO gas plus O2 gas. Well, I can cancel one of the O2s, right? And that leaves me with just one O2 right here. So this is going to be one O2. There's no O2 on the other side. And so what's my delta H for this one? I'm just adding reaction 1 and reaction 2 here. This is going to be 2x minus 1. Okay? So the answer here is B. That's Hess's law. Alright. Now, it's going to be very cumbersome to list the delta H for each and every possible reaction that you can think of. So, as a way of condensing all of this information about heats of reaction, we define what are known as standard enthalpies of formation. Okay, so you'll notice the symbol for that has an F instead of an R between delta and H. Okay, so this is the symbol for standard enthalpy of formation. This particular delta H refers to the delta H for a reaction where the product is 1 mole of whatever it is you're interested in. Okay, and you're forming it from the elements in their standard states. Okay, So the element is said to be in its standard state if it is in its most stable form at a given temperature. So for example, at room temperature, the most stable form of oxygen is O2 and it's gaseous. So O2 gas is a standard state for oxygen. Standard state for nitrogen is N2 diatomic gaseous form. What's the standard state for iodine at room temperature? Diatomic solid. Bromine, what's the standard state? Diatomic liquid. Okay. Carbon, what's the standard state? Graphite, solid, not diamond. Okay. And values of these standard enthalpies of formation are tabulated, and so that we can easily calculate delta H for any reaction. And how are we going to do that? Well, before we do that, let's just clarify the definition of standard delta H of formation. Okay, standard enthalpy of formation. Which of these is For which of these reactions is the standard reaction enthalpy equal to the standard enthalpy of formation of ammonium bromide solid? What did we say the definition of standard reaction is? Standard formation reaction. You form 1 mole of whatever it is you're interested in, right? So we're interested in ammonium bromide. So which one of these can we eliminate? This one right here. Okay. We need 1 mole of whatever it is we're interested in. And we want it from, so here you have 1 mole of NH4Br solid, 1 mole of NH4Br solid, 1 mole of NH4Br solid. We want it to be formed from the elements in their standard state. What's the standard state of nitrogen? Diatomic gas, so it can't be this one. All right. What's the standard state for hydrogen? H2 gas, so it can't be this one. What's the standard state for bromine? Diatomic liquid, so it can't be that one, right? So this one's wrong. What about the second one? Is that correct? Bromine should be liquid. Okay, so that's wrong also. So the correct answer is this last one. Okay. Note that you may have to use fractional coefficients like 1/2 N2 here to balance your equation, because you have to have 1 mole of the indicated substance or whatever it is you're interested in on your product side. For the delta H of that reaction to be called a standard enthalpy of formation. Okay, for which of the following is delta H of formation equal to 0? N gas or N2 gas? What's the standard formation reaction for this? You're going to form nitrogen gas from what? N2 gas. And so what would be my coefficient? No, I have to have 1 mole here. I have to have 1/2 N2 there. What would be the reaction that's associated with the formation of this? I have to form N2 gas from N2 gas. So which of these will have a delta H equal to 0? This one. To form N2 gas from N2 gas, you do nothing. So, in other words, by definition, the standard enthalpy of formation of an element in its standard state is 0. Okay. So for which of the following is the delta H of formation equal to 0? I gas, I2 gas, I2 liquid, or I2 solid? Iodine solid is diatomic under ordinary conditions, right? Solid and diatomic. So that's the standard state of iodine at room temperature. For which of the following is the standard enthalpy of formation equal to 0? Carbon graphite, carbon gas, carbon diamond, carbon C60. Graphite. Okay. It's the most stable form of carbon. All right. Now, like I said, the reason we wanted to tabulate delta H formation for formation reactions is because from those values you can easily calculate the delta H for any other reaction. All right? all you have to do is, to get the delta H for any reaction, is add up the delta H formation of the products and subtract the delta H formation of the reactants. Or you can say the negative of the delta H formation of the reactants plus the delta H formation of the products. Why is that? You're given that formula in freshman chemistry, but what's the rationale for that formula? Think of it this way. You have your reactants, right? And you want to change it to products, correct? Well, if I know the delta H formation of reactants, so I can go look at it this way. If I want to put elements in their standard state, okay, and I were to change it to reactants, a reactant, what's my delta H for this? That's just the delta H formation of the reactant, correct? If I have elements in their standard state and I want to change it to products, what's the delta H for this? So let me call this reaction 1, reaction 2. What's the delta H for this one? This would be the delta H formation of the product, right? So how do I use Hess's law and to manipulate these two equations so I can get my overall equation, the equation I'm interested in? What would I have to do with equation 1? I have to flip equation 1, right? I want reactant on the left side. I want this on the left side, so I have to flip equation 1. And then I combine the two. So in other words, I can say that my overall delta H is just negative of delta H1 plus delta H2. But what is negative of delta H1? That's the delta H formation of my reactants, and delta H2 is just the delta H formation of my products. So you can see where that formula comes from. It's a delta H formation of products minus the delta H formation of reactants. That's really just an application of Hess's law, which is just an application of the fact that enthalpy is a state function. So let's apply that to this equation right here. Delta H formation. Let's say the delta H formation of methane, oxygen, carbon dioxide, and water are W, X, Y, and Z. What's the delta H for this reaction? Sorry, in kilojoules per mole. So what should we do? Products minus reactants, right? So let's start with negative of the reactants. So methane is W per mole. You have 1 mole of methane, right? So negative W, okay, plus oxygen is X per mole, so times 2 moles, so 2X, negative 2X, plus carbon dioxide is Y, so 1 mole of carbon dioxide times Y, plus water, you have 2 moles of water, and it's Z per mole, so 2Z. So the answer is negative W minus 2X plus Y plus 2Z. So this is delta H formation of products minus delta H formation of reactants. And you just add those. Okay? Now, can we simplify this? What do we know about X? O2. It's delta H formation of O2. O2 is an element in its standard state. So that would be 0, right? So I can just remove that. So it's just going to be Y plus 2Z minus W. Now, where can you look up delta H formation? There should be tables in most textbooks. Okay, on your exam, you'll have access to that table. But if you want a more general source, you can go to the NIST website. So you go to webbook.nist.gov and then click on NIST Chemistry Webbook. You specify the formula. Let's see, let's say we want methane, so you enter CH4, gas phase, thermodynamic data, click on search, and here's the delta H formation of methane gas here. Okay, delta H formation gas is negative 74.87. So let's record that number. So for methane is, what's our value for methane? W, right? So for methane is negative 74.87 kilojoules per mole. Okay. What else do we need? Carbon dioxide. Okay. Carbon dioxide. So check gas phase there. Search. And there's your carbon dioxide. Delta H formation of carbon dioxide is negative 393.51. Okay, negative 393.51. So that's Y. Okay. Negative 393.51 kilojoules per mole. What else do we need? Water. So let's search for water. So H2O. And then we want condensed phase, right? So check condensed phase over here. Search. And the value for water is H2O liquid is negative 285.83. Okay. So our C is negative 285.83. And what would it be for oxygen again? Let's just verify. O2 gas. Check gas phase, uncheck condensed phase, search. And you can see there isn't one. Why? Standard state, it should be 0, right? So it doesn't even give you the number. Because there isn't any experimental value for it because it's defined to be 0. Alright? So those are your values. So what would be our delta H for this reaction? Standard delta H for this reaction? Equals, okay, it's negative W, so negative of negative 74.87. Okay, so actually what you have to do is you have to say negative of 1 mole, okay, CH4 times negative 74.87 kilojoules per mole of CH4. Okay, you really want to be thorough with the way you handle units. And then, so it's negative W, and then plus Y. So you say plus 1 mole of Y, 1 mole of CO2. So you say plus 1 mole CO2 times Y is negative 393.51 kilojoules per mole of CO2. Okay. Plus, what's the last one? 2Z. 2Z is 2 moles of water, right? So 2 moles of H2O times negative 285.83. 83 kilojoules per mole of H2O. So moles cancel out, moles of water. So your answer is in kilojoules. Okay? And this is kilojoules per mole of reaction. So how much is that? Let's calculate. Let's bring up MathCAD. Okay, so we have, oops. Negative of negative 74.87 plus negative 393.51 plus 2 times negative 285.83. That gives us negative 890.3 kilojoules. Okay, so negative 890.3 kilojoules. Should that be negative? Do we expect that to be negative? Do we expect a combustion reaction to have a negative delta H? Combustion reactions are burning reactions that produce heat, exothermic reactions. In fact, that's a very highly exothermic reaction. Okay, so here's an example type of calculation you might have to do based on your laboratory experiment. You'll determine the heat of combustion of an organic compound. Okay, so if you have an organic compound, like let's say benzene, okay, if you burn it, your carbon ends up being carbon dioxide. So that's what combustion reactions are, right? The elements, you get the oxides of the elements. And what's the oxide of hydrogen? Water. Okay? So we know the delta H formation of carbon dioxide. We know the delta H formation of water. So we know the delta H formation of these two. What's the delta H formation of O2? 0. Okay, this one, you can measure this from bomb calorimetry. Actually, you can measure delta U from the bomb calorimetry data, and then from delta U, you can calculate delta H. Okay, so you get your delta U first, and then you get your delta H. So you know this, you know this, you know this, you know this. What can you determine? You can determine the delta H formation of your organic compound. Okay, you might say, why not just look up the delta H formation of C6H6? Well, the value of this is if you have a different or a new compound, let's say, then that's how you can determine the delta H formation of that compound, and then so you can just add that to your list of delta H formation, so that any other reaction that's going to involve that compound, you already have a value that you can use. All right? So what would be the delta H formation of C6H6 based on this? Is it A, B, or C? You want to work it out? How do we do it? What did we say the delta H was for this reaction? You can measure the delta H combustion is equal to X. So what's that equal to? Products minus reactants, right? What's the delta H formation of our products? 6 times the value for CO2 is Y. So 6Y. Okay. 6Y plus the value for water is 3Z. Okay, minus the value for the reactant is oxygen, you don't worry, right? So C6H6 would be the unknown, what you're looking for. So let's call that minus delta H formation of C6H6 liquid. So how do I solve for delta H formation of C6H6? What would it be? Delta H formation of C6H6 is just equal to 6y plus 3z minus x. Which of these choices is the correct answer? 6y plus 3z minus x. Okay. That would be the delta H of formation, standard enthalpy of formation of benzene. Okay. And I already explained the basis of the calculation in terms of Hess's law, so we can skip that. All right. Delta H formation for ions in aqueous solutions. By convention, okay, you cannot, since you cannot really form just one single ion in solution, right? It always has to come in pairs, at least. You have a positive and negative. So by convention, we assign a value of 0 for the delta H formation of H plus in water. Okay? So in aqueous solution, delta H formation, so this is something you need to know. That's a definition of the standard enthalpy of formation of H plus in water. So if I were to say, let's say this reaction right here, 1/2 H2 gas plus 1/2 Cl2 gas gives me HCl aqueous. Okay? Let's say the delta H formation of that is X. Alright? And let's say I determine the delta H for the reaction of sodium and Cl2 gas to form sodium chloride aqueous is Y. Based on this information, can you calculate delta H formation of sodium ions and chloride ions in terms of X and Y? Let's see. Let's write the net ionic equation for this. Let's look at the first one. 1/2 H2 gas plus 1/2 Cl2 gas gives me H plus aqueous plus chloride aqueous. Okay. What are the delta H formations for these? For H2, what is it? H2 gas, 0. Cl2 gas, H plus, so Cl, well, that would be delta H formation of Cl, right? Chloride minus aqueous. So, how are these related to X? We said if you were, let's say you could measure that to be X, what would you say then? Then you say X is equal to delta H formation of chloride aqueous plus 0 minus 0 plus 0. So, whatever that X is, that's just the standard enthalpy of formation of chloride. Okay? So, this is in fact the standard enthalpy of formation of chloride. If you could measure that X, that would be the standard enthalpy of formation of chloride. How do you get the standard formation enthalpy of sodium chloride, of sodium ions? Let's rewrite this second equation using ionic equations. Keeping in mind that sodium chloride is ionized in water. Then you would say sodium solid plus 1/2 Cl2 gas gives you sodium ions and chloride ions. The delta H for that reaction is Y. Okay. So let's tabulate the delta H formations. Delta H formation for sodium, pure sodium, what's the value? Standard enthalpy of formation of sodium is element in standard state, pure element, 0. Cl2, what is it? Cl2 gas, 0. Sodium ions, that's what we're looking for, right? Delta H formation of sodium ions in aqueous solution. What's the value for chloride? We determined that earlier to be X, right? So we can say then that delta H formation of sodium ions plus X minus 0 plus 0, this whole thing is equal to the delta H for the overall reaction, which is Y. So that's equal to Y. So delta H formation of sodium ions is just equal to Y minus X. So you can see, by doing a series of these reactions, you can figure out delta H formations for different things. And so all you really have to do eventually is tabulate all of those delta H formations, because from those you can calculate delta H for any other reaction. All right. So let's make this your homework. Delta H formation of magnesium. I want you to actually show your work to figure out the delta H formation of magnesium ion. Okay?
What size?
42. Now, let's look at the molecular interpretation of heats of reaction. Why does the temperature change when a reaction occurs? Well, if you remember your potential energy of interaction between two atoms. Okay. In general, you say that the potential energy of interaction looks like this versus distance, right? And so if you have the shape of this potential energy curve looks like a well, so you could say that bonded atoms are trapped in a potential well. And so if you have two atoms that are bonded, you would say that they would be oscillating between this distance right here and this distance. Okay, so you say that they can't separate from each other. What would allow you to break a bond? Third body has to collide with this pair of atoms so that it would have enough energy to separate, right? So we say bond breaking is endothermic. Okay, to break a bond, you have to be endothermic. If you have atoms that are separated to begin with, they're not going to stick together if they collide. The only way they will stick together is while they're this close right here. Okay, where they're at this, let's say at this particular distance over here. A third body comes in and removes the energy from them so that the total energy drops from that to that. And that would allow them to be trapped in the potential well. So bond formation is exothermic. A third body has to carry that kinetic energy away as kinetic energy. So we say in bond formation, okay, there's a drop in potential energy. There's going to be a net increase in the kinetic energy, so it gets hot. So if the only thing happening in a reaction is bond formation, your reaction mixture gets hot. So let's imagine you have a collection of oxygen atoms. Okay, if they're all going to form O2 molecules, they're going to pair up to form O2 molecules. That extra energy has to go somewhere. This must be carried by other atoms. That will be like the atoms in the walls of the container. So your container gets hot. Okay, so bond formation is an exothermic process. For two atoms to form a bond, they have to lose energy. And that lost energy becomes kinetic energy of a third body. So you have conversion of potential energy to kinetic energy in bond formation. Similarly, in bond breaking, if you are to break a bond, that has to be an endothermic process. They have to get, if they're trapped down here in this potential well, they have to get energy from a third body in order for them to separate, to dissociate. So a third body has to provide energy to bonded atoms, and so the net effect is the third body loses energy. So like they could be getting it from, let's say, the container. So at the end, if you have a reaction that spontaneously occurs that happens to be endothermic, then the container, the atoms in the walls of the container would be providing that extra kinetic energy to cause the bonds to break. Okay? But reactions in general involve bond breaking and bond formation. Okay, so when a reaction occurs, you need energy to break existing bonds, and you need energy to form new bonds. So if you were to monitor potential energy as a reaction progresses, what would happen? Potential energy would increase, right, to break the bonds, and it would decrease to form when bonds are formed. Okay, so if this level right here involves all bonds being broken, then that's what happens. But in general, that's not the actual path that the reaction takes. It doesn't a reaction doesn't necessarily mean that bonds get broken first and then bonds get formed. Okay? During a reaction, what could happen is there could be partial breaking of some bonds and partial formation of some bonds. You get what's called an intermediate transition state, or in my form also intermediate states. So you have that transition state, and so the real process would not involve as much energy as you don't necessarily have to break the bond. So this might be the energy you need to break the bond. The reaction may not require that much energy to get it going. So this minimum energy that the reaction needs in order for it to occur is called your energy of activation. Okay, so but the delta H you calculate, which is the difference, which can be just approximately the difference between the potential energy of the reactants and the products. Okay, that is that is a state function. Enthalpy is a state function. So it doesn't matter if you imagine breaking all the bonds first and then forming the new bonds. Okay, you still get the same delta H. So energy is needed to break existing bonds. Energy is released when new bonds are formed. So bond breaking, okay, you need energy to raise the potential energy, and then bond formation, you release energy. So your potential energy becomes kinetic energy. So if more energy is released, then the extra energy just becomes kinetic energy of the products and the surrounding molecules, and your temperature increases. You say your reaction is exothermic. So this would be an exothermic reaction right here. Okay. So think of this diagram. Let me show you a better diagram. This would be the so if this was to scale right here is the progress of the reaction, and you have your potential energy here, reactants, products. Okay, this might be the kinetic energy right here of your reactants. Okay, once you get to the product side, if this is the kinetic energy of the product, this extra energy right here, okay, would have to be that's released to the surroundings, so becomes kinetic energy. So the net effect is you have conversion of potential energy to kinetic energy if you have an exothermic reaction. Okay. Now, if you have an endothermic reaction, what would the potential energy profile look like? It would look something like that. Okay, so this difference right here would be your delta H. Okay, it would have to absorb energy from the surroundings in order for it to produce products at the same temperature. So if this was the kinetic energy of the reactant and you want the product to have this much kinetic energy as well, okay, then this difference right here, which is going to be essentially this difference, would be the amount of energy that has to flow into your molecules, into your atoms, in order to convert your reactants to products. That's the molecular interpretation of heats of reaction. Okay. So classify the following as endothermic or exothermic. And what would be the algebraic sign of delta H in each case? Let's look at the first one. What happened there? CH4 gas breaks up into carbon atoms and 4 hydrogen atoms for each CH4 molecule. Exothermic or endothermic? What's the only thing happening there? Bond breaking. So delta H is positive or negative? Positive. Positive. It's endothermic. This process, for this to happen, you have to be providing it with energy from the outside. How about this one? Delta H for this. Two iodine atoms forming an I2 molecule in the gas phase. This is an exothermic reaction. Okay, a third body has to carry the energy away in order for your two iodine molecules to get stuck in a bond. Okay, it's an exothermic reaction. How about this one? 2I gas to I2 solid. Even more exothermic, because now to get your I2 gas to come together closer to each other to form a solid is also exothermic. That would be the opposite of sublimation, which is also exothermic. So delta H for this is also negative. This is also an exothermic reaction. Okay. What time do we have? Okay, got plenty of time. Bond energies or mean bond enthalpies can be used to estimate delta H of reaction for gas phase reactions. Okay, so for example, H2 plus Cl2 gas gives you 2 HCl gas. You can calculate the energy needed to break one HH bond, and then the energy needed to, you can look these up, okay? The bond dissociation energy to break one Cl-Cl bond, and then if you define Z as the energy released when HCl bond is formed, then delta H for this reaction is just X plus Y minus 2Z. Why is that? This is the energy needed. So if X, Y, and Z are just absolute values, these are positive numbers, okay? So this is the energy needed to break the HH bond plus the energy needed to break the Cl-Cl bond. How many HCl bonds are you forming here? 2, right? So minus 2 times the energy needed, energy released when an HCl bond is formed. So there's a negative there because bond formation is exothermic. So it's really just the sum of the bond energy for dissociation, for bond breaking, right? Sum of the bond energies for breaking bonds minus the sum of the bond energies associated with the bonds that are formed. So bond formation. So this works really well for gas phase reactions for estimating. So let's look at this. The reaction enthalpy can be estimated using bond energies for which of these reactions? A or B? What's the difference between these two reactions? This one's a liquid and that's a gas. Everything else is the same. So what's the answer? Bond energies, you can only use that to estimate delta H for gas phase reactions. Everything in the gas phase. Okay, so answer is B. Which one? This one? This is all gases. Oh, that's because, because you know that if you want to go from gas to solid, that it's going to be exothermic as well, right? And we're just predicting algebraic signs, so we're not actually calculating. What I'm saying here in the case of bond energies, you can actually calculate because you can look up these bond dissociation energies. Okay, these can be experimentally determined. Actually, what's done is you experimentally determine this. The numbers you look up is actually just an average for these bonds as they are found in different molecules. And so that's why it's an estimation, because it's not always going to be the same. For example, in a CH bond, when you're doing CH4, okay, if you break the first CH bond, okay, that will take a different amount of energy as opposed to breaking the second CH bond. Let's see. So you're gonna get CH2 here. Okay. That's the second CH bond will have a different, and you'll need a different energy. It'll require a different amount of energy to break as opposed to the first CH bond. So the numbers that you actually found tabulated as for bond energies for estimation purposes, those are the average of these 4 CH bonds. It's not really just these 4 CH bonds. You have a whole series of different molecules that it's based on. So that's why they're really just estimates. All right, so let's consider this reaction right here. Methane plus oxygen gives you CO2 plus 2H2O. Okay, let's say we've looked up the bond energies to be W for CH bond, X for a double bond between 2 oxygens, Y for the double bond between carbon and oxygen, and Z for an OH bond. What's the delta H for this reaction in terms of W, X, Y, and Z? Okay, so how many CH bonds would you have to be breaking here? 4, right? Your methane is CH4. You have 4 CH bonds. So you're going to have to need your delta H will have to involve a term that says 4W, right? So you can eliminate choice A and B right away. But let's finish this up anyway. Let's verify that C is in fact correct. Oxygen. How many oxygen bonds would you have to break? What's the lowest structure for O2? So that's 1 oxygen double bond, and you have 2 of those. So you're going to need 2X, right? So this is the delta H for bond breaking. Okay, what would be the delta H for bond formation? Okay, how much energy would be released in forming carbon dioxide? What's the lowest structure for carbon dioxide? You got 2 C double bond O's. So how many CO bonds are you forming? You have 1 CO2, so 2 CO bonds, right? 1, 2. So that's going to be 2Y would be released, so you have to put that as negative 2Y. So minus 2Y. And then how many OH bonds are you going to form? What's the structure for water? HOH. How many OH bonds? 4 total. That's you got 2 water molecules. So you have HOH. So you have 1, 2, 3, 4 OH bonds. So 4Z. Okay. So OH bond energy is Z. So minus 4Z. So that would be your estimated delta H for that reaction. Okay. Now, what about delta H at other temperatures? Well, to determine the delta H at temperatures other than 298 Kelvin, then you have to use the fact that H is a state function. So what you have to do is imagine your reactant at temperature T, the temperature you're interested in. Okay? Cool it down or warm it up to 298 Kelvin. You can calculate the delta H for that. What's the delta H for step 1? No chemical change. All you're doing is changing the temperature. What's this delta H? It's just going to be Q. It's integral of Cp dt from whatever T is to 298, right? So let me write that down here. Delta H for step 1 is just integral of Cp of my reactant, right? dt from from whatever temperature I'm interested in to 298 Kelvin. Okay? Then, now that I have I imagine doing that. Now that I have my reactant at 298 Kelvin, I imagine carrying out the reaction at 298 Kelvin. So from my reactants at 298 Kelvin, I get my products at 298 Kelvin. What's the delta H for this one? This second step right here, step 2. Delta H for step 2 is delta H formation of products minus delta H formation of reactants. Okay, because the numbers that you'll find tabulated for standard formation enthalpies are done at 298 Kelvin. So the strategy is Bring your reactant to 298 Kelvin. Imagine the reaction happening at 298 Kelvin, and then what's the last step? Now you imagine taking your product from 298 Kelvin down to or up to whatever temperature you were interested in to begin with. What's delta H for step 3? Delta H for step 3 is equal to integral of Cp of our product dt, okay, from, this time you take it from 298 Kelvin to T. So the total delta H would be integral of Cp reactant dt from T to 298 plus delta H reaction at 298 Kelvin. So I'm going to say this is the delta H at temperature T plus integral of Cp dt of the product, and you have to realize you have to add this out for all the products and add this first term out for all the reactants multiplied by the actual moles in the balance equation. And this is going to be from 298 to T. Can I simplify this? Can I combine those two integrals? If I want to combine those two integrals, I have to have the same limits, right? So I can flip the limits for this one. Integral from 298 to T. So this is going to be negative Cp of reactants dt plus delta H formation at 298 Kelvin plus integral of Cp of products dt from 298 Kelvin to T. What do I do now? I can combine these two, and that gives me what? Integral of Cp products minus Cp reactants dt from 298 to whatever temperature I'm interested in plus delta H of my reaction at 298 Kelvin. Okay. This is the formula for the delta H of the reaction at temperature T. Since T right here is really just a dummy integration variable, I can put a prime there since I'm using T as one of my limits. So that is known as Kirchhoff's law. Kirchhoff's equation. The whole idea there is you have reactant at some temperature T besides 298K. Imagine heating or cooling that reactant to 298K. Now imagine the reaction happening at 298K so that you now have products at 298K. Then imagine changing your products, heating or cooling your product back to the temperature that you want. If you did all of that, calculate the delta H for each one of those steps, then you get the delta H for the overall reaction. Okay? And so that's pretty much it for thermochemistry. That should be enough setup for you to be able to do lab experiments and